All right, I'm gonna have you try number 5 here on your own. So you can go and pause and work through this one. All right, so you can check your work there with a 99% confidence in a sample of 30. The number of minutes a patient will wait for a treatment is between 152.4 and 196.2 minutes. All right, and then here is an example. One of the ones we worked with the applet the other day of creating those samples and seeing the intervals and how many of those intervals included the parameter or the true population mean. You can see here 100% of the samples that were taken included the population mean, and so this is really good. A couple were close, and we saw as we increase this, you might have a few that go out and eventually land around 95%. Right now it's 100% hit rate, and we saw as we increase, we got closer and closer to that exact confidence level. All right, so as we look at 6 here, we have the following data represented in a sample of assets, 30 credit unions in southwestern Pennsylvania. Find 90% confidence interval of the mean if the population standard deviation is 14.405. So let's write down some of our known. All right, so n equals 30. Work through that. You can find the sample mean. Save you some time, 11.09. Confidence interval we're looking at is 90%. Standard deviation, 14.405. And then we need to find our z alpha 2. So our mean was 11.09. Standard deviation, 14.405. And then we want the central, and we want 0.90. And so there's our z of 1.645. All right, so then if we take that, all right, again, we're looking at this distribution. We want that middle 90. And then as we calculate that using our formula, so you can double check your work here, our interval is going to be between 6.764 and 15.416. Now 7, it says for the above problem if the sample size was 3, so we went from 30 to 3, what would be our new interval? So remember in the formula you have standard deviation over the square root of n. So instead of that being 30 like in the original, it is now 3. So if you have that in your calculator, easy to switch that out, and we end up with negative 2.59 to 24.77. So as we saw when we're playing around with the applet the other day, as we decrease our sample size, it increases our interval. So those are opposites of each other. And then 8, now we're looking at 300. So if we increase our sample size, what happens to our interval? It's going to decrease because they have more data to work with, so we can be more pinpoint accurate with what that interval is. And we end up with 9.722 to 12.458. Okay, using the same formulas, all we're doing is switching out our n value, but you can see how sample can affect our data there. So number 9, does sample size matter? Yes, it does. As sample increases, our interval decreases, or vice versa. and last little concept here, sample size. How large of a sample is necessary to make an accurate estimate? The answer is not simple. Depends on three things: margin of error, population of standard deviation, and then degree of confidence. So how close to the true mean do you want to be, and how confident do you wish to be, right? That varies. So we have a formula for sample size that's derived from the error formula. All right, so we've seen this. And so what we're going to do now to figure this out is we're going to solve for n. Okay, I'm going to do this for you. You don't have to worry about doing the work here. Once we solve for n, we end up with this equation. So now we can use that and put it to find the n, or the sample size that we need. So let's apply it. All right, so 11, scientist wishes to estimate the average depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. Scientist wishes to estimate the average depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. From a previous study, the standard deviation of the depths measured was 4.33 feet. How big should his sample be? All right, so we need to find that. So we're going to take our equation again. So we're going to take our equation here and input the information that we know. Standard deviation is 4.33 squared wants to be within 2 feet for our error. I'll label these all over here. And then what we don't know is our z alpha 2, but we have our 99, so we can take that. Okay, so mean at 0, standard deviation of 1. We plot it, we get 2.576. Then we could just simplify that, and that equals 31.103. And so we'll put that at 31.1 feet. All right, and then a couple cautions here. Confidence levels are not probability. So a confidence level such as 90% is not a probability. Saying we're 90% confident, the mean is between 21.1 minutes and 21.3 does not mean that there is 90% chance that mean is between those two values. If I were to take 100 sample means, 90 would contain the actual population and 10 would not. And the last few things here. Mean is a fixed number, right? It's the true population. It's either in the confidence interval or not. Incorrect, there's a 90% probability that the actual mean is in the interval. But the correct one, if a large number of samples is collected and a confidence interval is created for each sample, approximately 90% of these intervals will contain mean. And that is what we need to focus on. 90% of these intervals will contain the mean in a large number of samples. When we answer questions about confidence intervals, we interpret with complete sentences. And another example, in the long run, 9 of every 10 such intervals will contain. But again, that's in the long run. So you do 10, all 10 could hit. You do 10, 7 could hit. In the long run, 9 out of every 10 will hit.